Thank you, Nadav.
Thank you, Amnon.
Well, whether my talk is going to be a treat, it's yet to be seen, but I'll try to do the best. I'm coming from machine learning, computer vision, machine learning, theoretical side of machine learning. And in the past 2 years, together with my students in the lab, we found very, very interesting connections between the most exciting part of machine learning today. It's deep networks, between neural networks and quantum mechanics, especially how do you represent many particle wave function, quantum entanglement. Many of the recent results from physics are very relevant to understanding deep networks. And the tricks being employed by machine learning practitioners and deep networks are becoming quite relevant to simulating complicated physical systems that are very difficult today but can become quite manageable using the tricks from machine learning. So I thought to share with you a bit of those results. Work of my students, Nadav Cohen, he's doing now his postdoc at the IIS in Princeton, Institute of Advanced Studies. Yoav Levin completed his master's at Weizmann Institute in physics, in quantum mechanics and condensed matter physics. Or Sharir is a computer scientist. All of them are PhD students, and they're my co-authors and actually leading this area. So some of the publications are in machine learning venues like ICLR, and also one of the results is under review at PRL. So it's all very relevant, and that we have many ongoing results that are not yet published, but I think there is enough to show that there is something quite exciting, kind of a bridge between two different communities that we can bring together. But before I start with how all of this relates to physics, I'll spend some time, 10, 15 minutes, about machine learning. Explain what are the mysteries that we have today in machine learning, especially the deep networks. What is this disruption that is ongoing with deep networks? And then I'll start connecting it to quantum mechanics. So today, almost all industries, they want deep learning. For example, what Mobileye is doing is all deep networks. All the calculations of perception, of detecting vehicles, pedestrians, traffic signs, traffic lights, lanes. It's all image in, video in, going through a deep network and results out. All the decision-making in the car, for example, deciding when to change lane, how to plan a trajectory, how to negotiate with other vehicles. It's all deep networks. It's all machine learning. Most of the stuff, the services you have today from Google, from Apple, whether it's Translate, whether it's Google Photos, whether it's pattern recognition, it's all deep networks. All the stuff that Facebook is doing in terms of the rule of the algorithms, it's all deep networks. So deep networks today is a fundamental tool, and today people call it artificial intelligence. So when people say AI, they basically mean deep networks. So let's look a bit at the mystery of these deep networks. So let's start with some basic definitions. We have the input space, X. So the input space could be an image, say 100 by 100 pixel image. And the output space, it's called the labeled space. Let's assume we want to do pattern recognition. So input would be an image, output would be, is the image an image of a face or not? So it will be two labels, face or not face, or could be 100 labels. Tell me which category is this, a face, a car, a pedestrian, and so forth. So this is the input-output of the system. Then there is a distribution, and the distribution is unknown, where you have input and label. It's coming from some unknown distribution. And then you have a loss function. Say you have a predictor, you have an input in, the prediction predicts what the label would be. In this case, it's let's call it y hat. And you have a loss function that if the true label and the predicted label are different, you get a penalty. And that's the loss function. And then the task is you are given a training sample, which is sampled from this unknown distribution. So we'll have pairs of input-output. This is the xi, yi, and they are drawn from this distribution. And the learning task is to predict a function, a mapping from input to output, that minimizes the expectation over the loss. Okay, over the loss of this training set, or over the loss of the entire distribution. Now, the way to do that, since the distribution is unknown, you use a training set. So you do two things. One is you constrain the space of possible solutions. This is called the hypothesis space, because if you don't constrain the space of possible solutions, you can overfit. You'll be basically creating a solution that fits the noise rather than fitting the signal. Right? Imagine that you have, in a 2-dimension, you have a collection of dots, and you want to fit a polynomial. So if you have n dots, you can always fit an n-degree polynomial, but it will basically are fitting to the noise because the dots are not located precisely on this 2D space. So you need to constrain yourself. And that's the hypothesis space H. And then within this hypothesis space, you want to find a function that will minimize the empirical loss, the loss over the training set. Okay, so this is, in one slide, what is the task and approach in machine learning. So now, what is the complication? So this slide shows us the following. F star D is the true function. We don't know this function, but this is the true function. H star D is the function over the hypothesis space. Remember, we constrained ourselves. We're not looking for a mapping over all possible input to output mapping. We're looking for a mapping inside this hypothesis space. So H star would be the optimal solution in that hypothesis space. And again, the distribution is unknown, so it's very, very difficult to find this at this point. HS star is the optimal under the training set. So this is something that there is a chance to find. Okay? And H bar is what the algorithm gives us. Why the algorithm may not always give us H star, HS star is because the energy landscape could be nonlinear. If the energy landscape is nonlinear, when I do an optimization, there could be many local minima, and I get trapped in one particular local minima. So I may be here rather than here. So now if we look at this, we say the following. This is called approximation error. So the bigger the approximation error is, it means that we are less expressive. We would like a learning machine that is as expressive as possible. So we would like these two to be as close as possible. Right? This is called estimation error, or the generalization ability of the system. If this is large, it means that we are probably overfitting the data. We would like this to be quite small. Right? If we are quite small, it means that even though we trained from a training set, the solution that we got will generalize to unseen examples. So we would like this to be as small as possible. So we like this to be as small as possible, this to be as small as possible. And this would be the training error. This will have an error if we're talking about a nonlinear optimization and we're not guaranteed to find the global minima in this landscape. Okay? So now, what do we know about this? That in classical machine learning, the hypothesis space is linear, and there are tricks to create nonlinear hypothesis space using linear methods. And really, the engine is called support vector machines. Now, in this classical stage, we have the following. So again, we go to this slide. We have first the empirical loss. So these two, the training error is 0 because it's a convex problem. And we see the following. If we expand the hypothesis space, we're reducing the approximation error. We can even see this visually. So we're reducing the approximation error, but we may increase the estimation error. That means our ability to generalize is weakened. Right? If we shrink the hypothesis space, we are increasing the approximation error. That means we're reducing our expressibility, our expressiveness of the engine, but we may improve the estimation error. right? We're kind of shrinking this, okay? And then all of this looks very, very reasonable, and all of this is a well-developed theory. So during the 90s and the 2 decades from the 90s and 2000, this was the main vehicle. The supported vector machine was the main vehicle for doing machine learning. Okay? Now, in the past 6-7 years, there was a kind of a resurfacing, reemergence of neural networks. And now I want to explain what is the mystery going on with these neural networks. So we have the neural networks are very simple to explain. You have the input, so each node here would be a scalar in our input vector. So if our input vector is a 100 by 100 image, we will have 10,000 nodes here, right? And then you have layers where each layer does a linear combination of the layer nodes preceding it, and then undergoes some nonlinear activation function, and that proceeds until we get an output. The output could be a single scalar, or it could be a vector as well. So this is a classical neural network. There is also a recurrent network in which the input is coming as a sequence rather at one step. Here the input is coming in one step. Here the input is coming through a sequence. Let's say you want to do text processing, so you have letter by letter coming one after another. And in the past 6-7 years, what is showing the biggest success is convolutional networks, which is a special case of fully connected networks with additional bells and whistles. One of them is pooling, where you are decimating. You are creating a calculation and then decimating using pooling, calculation, decimating, something like this. So what is the mystery? If we go back to what we see here, we have the following. First, we do have a training error because the problem is non-convex, right? Because you have a linear combination and a nonlinear activation function, linear combination, nonlinear activation function. So the entire landscape is highly nonlinear, and we want to find we want to optimize it, find a minimal energy, and because it's nonlinear, it's a non-convex problem. Therefore, we may end up here rather than here. With support vector machines, we were guaranteed to end up here. So that's not unique. Even if we did end up here, it's not unique. There are many local minima. Second, the observation is that if we do stochastic gradient descent, so rather than doing a gradient descent, we're sampling. Rather than when we're calculating the gradient, rather than using the entire training set for calculating the gradient, we're sampling a subset from our training set and calculating a stochastic gradient. That turned out to be very, very successful, and it somehow reaches one of those good local minima. And then the real mystery is the following, that some low training error, if we reach a low training error hypothesis, some of them generalize well and some do not. And it's really data dependent. And with the typical data, the stochastic gradient descent will succeed, will generalize well. It means that the estimation error is going to be small. And expanding the hypothesis space reduces approximation error as we expect, but opposite to our expectation, it also reduces estimation error. So in classical machine learning, if we reduce the approximation error, we might increase the estimation error. In deep networks, you are increasing the hypothesis space, reducing approximation error, but also reducing estimation error at the same time. Okay? And all of this is kind of not well understood, and it is a mystery. Okay, so this was kind of a short exposition of machine learning, and let's start connecting this to quantum mechanics and see how quantum mechanics is helping us. So we're looking at the convolutional networks, where you have your input, say an input is in an image. It undergoes convolutions, a number of convolutions. So this is a layer where each channel in this layer is a different convolution. After each convolution, there is a nonlinear activation. There is a decimation. For example, every 2 pixels would become 1 pixel here, or every 2 by 2 window would become 1 pixel in the decimation. Usually, it's a max pooling decimation. And then you continue. Convolution, nonlinear activation, decimation, until you reach your output layer. So this is the classical convolutional networks, and there has been a variety in the past 5-6 years. There has been a variety of modifications of this basic technique. They have different names, and they're all very, very successful in applications. Okay. So when we're looking at a convolutional net, it's a function over many local elements. So imagine an image, and you can divide the image into blocks, say 5 by 5 windows, whether they're overlapping or non-overlapping, it doesn't really matter. And those are your basic atoms, and your function is a function over those atoms. So let's describe if X is an atom, say a 5 by 5 piece of an image, Fi of X, where you have m such functions, computes a feature of that. So you'll have m features for each window. And then since we have n possible atoms, say you have a 100 by 100 image, 5 by 5 windows, right? So you'll have 20 by 20, you'll have 400, n will be 400 in this case, right? So you do a product of these, and so you have those n elements, which you can imagine those are n regions in the image. Then you can show that a function in this space can be written in this form. You are taking products of the functions. So you have m functions applied to n different regions. So you have kind of an n by m possible outputs. And you are making choices. You're making choices, and the coefficient, it's a linear combination where the coefficient is arranged in a multi-dimensional table where D goes from D1 to Dn goes from 1 to m because we have m such basic, some basic functions. And this multi-dimensional table is called a tensor. So it's kind of an extension of a matrix. Imagine a matrix is a 2-dimensional table, so now you have an n-dimensional table, and each axis has m possible values. So it's an m power by n number of entries. And you get this linear combination, and you can think of it as a dot product between this tensor and the function, and this function is basically a rank 1 tensor, which is defined here. So rank 1 tensor is just like a rank 1 matrix. A rank 1 matrix is an outer product of 2 vectors. A rank 1 tensor, say, that has n different dimensions, is an outer product of n vectors. Okay. Okay, so this is the dot product between them, and this tensor here fully determines the function h, because this is only a function of the input, and what determines the function h is this coefficient tensor. And this is the tensor that we want to start to investigate. So I'm gradually getting into many particle wave function. So in quantum mechanics, physicists have a tool to analyze tensors whose number of entries is exponential. And you want to analyze it using something whose size is polynomial. And of course, you can do that if there are constraints. And in physics, they are called a volume law, area law, where not all particles interact with all particles. And the way physicists do this is by creating a graph where each node of the graph is a tensor of a smaller dimension. So if the nodes of the graph, if you have a node that doesn't have any edges, it's a scalar. If you have a node that has a single edge, it's a vector. And the dimension of this edge, it's called the bond dimension, tells you what is the dimension of the vector. If you have a node that has 2 edges, it's a matrix. And if you know there are 3 edges, it's a 3-order tensor, and so forth. Okay? Now, to create a graph, you have nodes connecting to each other. If you have, so the connection between nodes is a contraction. It's a dot product on the edge between the 2 nodes. So if you have, this is a vector here and a vector here. This is going to turn, this is the dot product between 2 vectors, and the result is a scalar because there is no outer edge. So we're back to this. Right? You have here a matrix, and you have here a matrix, and they have a shared edge. So we are talking here about a matrix multiplication, and the result is a matrix. You see, you have 2 free edges, and so forth. So you have this graph. Each node represents some order of tensor, as you can see here, and then you start doing all the operation, the contractions, the dot products along the edges, and the result is a tensor whose dimension is the number of free edges that you have. If there are no free edges, it's a scalar. If there's 1 free edge, the result is a vector, and so forth. Okay? So this is the way that physicists use to represent tensors. Now let's go back to our problem here. Right? The functions in the space is a dot product between this coefficient tensor and a rank 1 tensor. So directly computing this is intractable because it has an exponential number of entries. So just computing it is intractable. So now we want to use the tensor network, and if we can look at tensor networks which are trees, this is a very popular tensor network in physics, gives us the convolutional nets. Give us convolutional nets in which the pooling is product pooling rather than max pooling, and the activation function is linear. And we call this convolutional arithmetic circuit, because at the end of the day you have only products and summations, so these are polynomials being computed in this network. The tensor network topology is the convolutional, is the conv-AC architecture, and the weights are spanning all the possible family of tensor networks. So if we look at this configuration, we have n regions or n inputs. So each of these is a matrix, right? It has two edges. This is a tensor which has zeros everywhere, and on the super diagonal has only 1, and all the rest is 0. So what this does, it does the pooling, and at the end you get you get a scalar because there's no free edge after this is being computed. So this is basically a rank 1 decomposition of the tensor. So a tensor, just like a matrix, can be decomposed into a sum of rank 1 vectors. A tensor can also be decomposed into a sum of rank 1 tensors. So you have outer product of n vectors, and then another outer product of n vectors, and another outer product of n vectors, and you do a linear combination of them. It's a way to decompose a tensor. So, and this can be represented as a shallow convolutional network, where you have your input. These are the n by m representation features. And then it goes through a convolution, then it goes through a pooling, and then another linear transformation, and you have your output. So this would be a shallow network, not a deep network. But we can take this same tensor and decompose it in a hierarchical manner. And this is the tree tensor network. So you are losing it in pairs. Right? So every pair of inputs here are being combined, and then a pair of matrices here are being combined, and so forth. So you're starting with vectors, creating matrices, then taking pairs of matrices, creating four-order tensors, taking pairs of four-order tensors, creating 8-order tensors, and so forth until you go. This would correspond to a convolutional network, to a deep network, where the depth of this tree is the number of layers you have here. Since we took pairs, it means that the pooling is done every 2 pixels is being decimated to 1 pixel as a product. Okay? So what we have here, we have the tool of tensor networks taking this general function and creating a network out of it, a convolutional network out of it, which is the kind of convolutional networks that machine learning practitioners use. Okay? So now that we have established this connection, we can start taking results from quantum mechanics and applying them to our field, and taking results in our field and applying them to simulating physical systems. So let's see how we're going to do that. Okay, so going back to this chart, let's look at what is called in machine learning inductive bias, and in physics it's entanglement. So let's look at that. So in machine learning, what we are interested is in representing connections or correlations between regions in the image in which we have prior knowledge that there are correlations. So for example, if we look at natural images, we know that neighboring pixels are correlated. Right? That's the idea of natural images. So if we're building a deep network, we would like that deep network to represent the fact that neighboring regions they're not independent, have a correlation, and we like the ability of that representation to be maximal. Otherwise, we'll not be able to be expressive enough to represent natural images. But let's assume that we're looking at faces. In faces, we know that there is a bilateral symmetry. Right? My left-hand side of the face is correlated to my right side of the face. So this is something that we can see here. So if we take our input regions and divide them into two subsets, our prior knowledge is what subsets we want to divide them to. For example, if you want to represent natural images, this would be the two subsets. And if we're talking about faces in which we have prior information that there is a bilateral similarity, this would be the two subsets. So our prior knowledge tells us which subset we want to divide. And then we would like our network or machine learning engine to have maximal expressivity to present correlations between those two subsets. Okay, so this is in machine learning. So what kind of dependencies convolutional nets model, and how do these relate to network architecture? How do I design my network to maximally represent correlations between those two subsets of regions, which my prior information tells me that those subsets represent the goal that I have in learning the phenomena that I want to learn. So now let's go back to quantum mechanics. So if you have a many particle system, right, they're entangled. It's another way of saying that they are correlated, that there are subsets that are correlated, right? So in a particle state is again represented as a linear combination of basis vectors. These vectors are in complex domain, but doesn't really matter, right? And if you have a system of n particles, you can see that it's very, very similar to what I've shown you before. You have here a tensor, coefficient tensor, and here you have an outer product of the basis vectors. Okay? So we're back to the same thing, and quantum entanglement measure, how do you measure dependencies between sets of particles? So now let's move on and see the following. Let's assume that we define two subsets, a subset I and the subset I complement, just like we did with images, right? We defined, like in a checkerboard pattern, on a bilateral symmetry pattern, we define two subsets. So the same thing here, you define two subsets, and you take your tensor and you can matricize it. So those two subsets they define two subsets of indices. Right? Because what are these subsets? These are subsets of the n indices. Let's say n is 10. We said 1 to 5 would be subset I, 6 to 10 would be subset IC. So now we can take the tensor that has 10 dimensions and say dimension 1 to 5 is one axis, and dimension 6 to 10 is another axis, and we create a matrix. Of course, the number of elements in this matrix is going to be exponential, but still a matrix. So this is called matricization. Okay? So we are creating a matrix out of the tensor given these two subset of indices. Okay? So we arrange it as a matrix. And then what we do, Okay, so we take, this is our system state. We matricize, we decided which are the two sets of particles, or we decided what is the set of particles because the remaining is simply the complement. And we have a matrix. And then we look at the singular values of this matrix. And quantum entanglement is a function of the singular values. So entanglement is measures, for example, entanglement entropy is you take the entropy function of the singular values and then you normalize it by the L2 normalization of the singular values. There's geometric measure. There is, simply take the rank. It's called the Schmidt measure. So it's a function of your singular values, tells you what is the correlation between the two sets of particles, and physicists call this entanglement. But it's basically looking at correlation. To make this message even more clear in terms of correlation, to make this more clear in correlation, let's go back to our function, right? And if this function is separable within respect to the indices, so again, I is a subset of these n indices. So let's imagine n is 10, I is 1 to 5, and I complement is 6 to 10, right? If this function is separable meaning that you can represent this function as a product of two functions. One is on the subset of the indices I, and the other one is on the subset of the complement. Right? And if it's a product, it means that this function cannot represent any connection between the two subsets. That means if there were correlations, it cannot represent it. Right? So the measure of entanglement is how far away we are from separability. So if we have low entanglement, it means that we're limited in representing the connections. High entanglement, it means that we are expressive. We can represent, right? And we would like the entanglement to be as high as possible if we know in advance that those two subsets are connected. So imagine in images, in the bilateral symmetry, we know that this part is connected to this part, so we would like our network to have the expressivity to represent this. So the same thing in quantum mechanics. High entanglement meaning that we can represent these kinds of connections. Okay, and the choice of entanglement measure determines the distance metrics, whether it's a Schmidt number, whether it's a entanglement entropy, whether it's a geometric measure, and so forth. So if we go back to our network, this is a convolutional net. And what I've shown you is that this convolutional net corresponds one-to-one with a tensor network, with a tree tensor network. I'll later say a few words about non-trees, okay? But it's a tree tensor network in which you have in the coordinate, see these are input elements, could be 5 by 5 region in an image. In the tensor network, these are the terminal nodes, which are the particles. The number of layers here, it corresponds to the depth of the tree. The layer width, the number of channels that you have here, is the bond dimension, the dimension of the arc, of the edge that you have. The pooling geometry, how do you decimate? Here is the connectivity of the network. So these two are being then decimated into this. So the way you decide which pixels you are going to then max pool is represented here in the connectivity of the network. And with overlaps, I didn't talk about overlaps. I'll talk about this. I'll talk about this later. Okay, so we have this connection, and when we look at the entanglement, so we have this subset I and its complement. We can represent the entanglement as a mean cut, where then we multiply the bond dimensions along the mean cut, separating I and I complement. Now, this mean cut would be very, very useful. This is a technical thing that when you talk about this node, again, I remind you, this node is a tensor. In this case, it's a 3-order tensor, which is 0 everywhere and has on the diagonal 1, and all the rest is 0 at a specific point. That only one edge matters. The other edge does not matter. Okay, but it's a technicality. Okay, so we can analyze the effect of the Conway C architecture on entanglements that we have here using a multiplicative mean cut. So let's see what kind of riddles we can answer here. So first, I'll talk about the riddle in machine learning, and then I'll talk about effects in physics. So in machine learning, one of the riddles that has been ongoing on for the past few years and has been resolved about a year ago is why depth matters. Why deep networks are so much more successful than shallow networks. Right? And the reasons that they're much more successful, and this is something that was open, is you can express in a deep network of polynomial size, you can express functions that would require a shallow network to grow exponential in terms of the number of parameters in order to represent the same functions. So again, a deep network of polynomial size would express functions that you'll require a shallow network of exponential size to represent. So how does this become apparent in all this picture that I showed you? So this is a shallow network. Remember that it's basically a rank 1, it's a rank 1 decomposition of your tensor. So when you're talking about the mean cut, since we said that only one edge counts, you're basically saying that the expressivity is the bond dimension that you have here, which means this is the number of channels you have in your hidden layer. If you want to be expressive, you would like the number of channels to grow, and it has to grow exponentially. On the other hand, in a tree network, right, when you are doing your mean cut, you basically, it's a multiplication of different nodes here, of different edges. So rather than putting all on one edge, you can spread it on different edges, so you get an exponential effect. So what you have here is that a deep convolutional network, which is this one, it can model dependency or entanglements, which requires a shallow one to have exponential width. Okay? So this solves a mystery that was going on for a number of years in machine learning. Okay? Let's go back. Let's go to recurrent networks. In recurrent networks, again, we're back to the same kind of representation. We're talking about the function, the coefficient tensor, dot product with a rank 1 input tensor. In recurrent networks, the input is a sequence rather than having an image where your n elements are regions in this image, where imagine you have text, where you have a letter after a letter after a letter coming in. So you have a sequence, and this is called a recurrent neural network. And because of the way we build it, we call this a recurrent arithmetic circuit. And this would correspond to a particular member of tensor networks, which is called a MPS, a matrix product state, which looks like something like this. So you have, these are your inputs. It goes through a matrix multiplication. You have an input from that side, goes through another matrix multiplication. There's a product here and continues like this until it goes to the output. Okay? So this is a matrix product state. But you can create a deep version of this recurrent network. So what is entanglement in this kind of case? In this case, entanglement, we call the start and entanglement. So you have a sequence, and you would like to have a memory. If you want to analyze a sentence, let's assume we're talking about natural language processing. In order to understand the sentence, you have to have memory. And the longer memory you have, the more inference, the better inference you can make. And memory means that you'd like to have correlations between the start of the sentence and the end of the sentence. And the question is how is your network, what is the strength of your network in modeling these kinds of long memories? And again, you can represent this through entanglement. Okay? So in the case of a shallow RNN, right, this measure of entanglement is simply the number of hidden channels R that you have here. So if you would like to have something expressive, R would need to grow exponential. So you need to have a network that has exponential size if you want to be able to be very, very expressive. But if you go to something deep, right, add another layer here, This would correspond to a network in which has duplications. We call this reuse of information. We're taking the particles and we're creating copies of them. What this creates, it creates a long-term, so in case of a shallow network, it will be linear in the number of parameters, but in case of where you have a deep network, it's going to be combinatorial, the number of parameters. So this is very, very similar to the depth effect we had in convolutional nets, where you had a polynomial size deep network representing a shallow network of exponential size. So the same thing in entanglement. Depth has a combinatorial effect. Okay. Let's look back into expressivity in physical systems. So this is a wave function of a n-body particle system. And there are systems in which they're called area law and volume law. So let's look at the 1D case. So we have here n particles, and let's assume that we decided that these particles is the subset A and all the rest is the subset B. So in terms of an area, volume law means that all particles here are entangled with all other particles. This would be a volume law. Area law means it's only the edges. So only these two particles interact with the other particles. So there are systems in which have volume law where it's highly entangled, and systems which are much lesser entangled, which are area law. And the question is when we go and represent this as tensors, what is their expressivity? Can we express volume law? Can we express area law? And then it turns out that these three tensor networks are kind of limited. So the leading tool is tensor networks. So what physicists do, because it's limited, so this is the three tensor network, they add loops, kind of create general graphs, and this is called MERA. They add disentanglers, but basically adding loops. So you're taking something that is limited, which is a tree, and making it much more powerful by having kind of a general graph. But the price that you pay, that it's intractable. What machine learning people do is when they do convolution, they have overlaps. These overlaps create a reuse of information, and in machine learning, one can prove that the overlaps in the convolution has an exponential effect in expressivity. What this corresponds to in terms of a tensor network is to create a tensor network with reuse of information, with repetitions. And this would create an effect similar to the effect you have with MERA, but this is tractable, where this is not tractable. So if we look at the results here, so this is the overlaps you have in convolution, and in RNN it's the depth, where the depth gives us reuse of information. This is in terms of the convolution, and this is in terms of the RNN. So again, the tricks in machine learning are very, very innocent. You're adding depth, and you're doing repetition. You're doing overlaps. If you now translate it into the world of tensor networks, this means that you're applying a reuse of information to create a mechanism which is, again, polynomial size, but has a much, much more powerful effect than a tree tensor network. And then the result is, so following, if you look at a deep recurrent net, it can support the law correction to the area law. So I said there are systems that have an area law, systems that have a phase transition. At the critical point, it's log of the number of particles. So this is log of the size of this subset. And this is something that can match the expressivity of MERA, but here we're talking about an engine which is tractable. If we look at the overlapping convolutional networks, it supports volume law, which is something which is very, very difficult to support. Again, volume means that every element is entangled with all other particles, and we can do this much more efficiently. The number of parameters is a square root of the number of parameters that other methods use, using, for example, reduced Boltzmann machines. It's polynomially more efficient than any other technique. So I'll end here and summarize the following even without slides. We took machine learning. The most successful engine in machine learning today is the convolutional net. I showed a mapping from convolutional net to a tensor network representation, which represent a n-particle wave function dot product with a product state, which is a rank 1 tensor, which is the input. And it's one-to-one. Means it's not similarity, it's identical. Once we have established this kind of bridge, this connection, we look at what machine learning practitioners are interested. They're interested in inductive bias. What makes a certain input successful to a deep network? As I said before, if you're looking at natural images, you're looking for correlations between neighboring regions. If you're looking at, for example, faces, you have bilateral symmetry. So you're looking for the ability of the network to represent correlations between regions of interest. In machine learning, it's called inductive bias. In quantum mechanics, it's called entanglement. And measures of quantum entanglement is a measure of correlations, in that case between particles. In machine learning, it would be correlations between the regions. Once we have established that, we can start taking results from quantum mechanics, like the quantum mean cut, use it in order to solve a riddle in deep networks, which is the depth. It's called the depth efficiency. Why depth matters. Where the result is that you can have a polynomially sized deep network which can represent functions that you need an exponentially sized shallow network in order to represent. Once we have established that, we can then make a contribution to the other side. We look at what physicists do in order to create more expressivity in their tensor networks. They add loops. The downside of adding loops is it's intractable. What do machine learning practitioners do in order to add expressivity? They add overlaps in their convolution, and they add depth in their recurrent networks. These are very, very simple tricks, but have an exponential effect in expressivity. We can then translate those tricks into the tensor network era, creating reuse of information inside the tensor network. And then we can start showing that we can represent area law and volume law as good as the Mera, where you add loops, and even better than that in terms of representing volume law. In addition, we have, all of this is published. In addition, we have unpublished results by taking systems in which simulator techniques are not good enough to represent those systems, and using techniques like this and additional techniques that we have developed, showing that we can get very, very good, lowest energy possible in critical systems in which today's techniques are not able to give you. So this bridge is very, very interesting to both communities, both from machine learning practitioners. We can take results that people in quantum mechanics and condensed matter physics have been developing for decades and start shifting them to machine learning. And we can take tricks from machine learning and see what we can do in order to simulate complicated systems in physics. Thank you.
Questions? Please check. Hard complex problems with non-trivial correlations occur also in classical systems, for example, in spin glasses.
No.
And in what way is deep learning more connected to quantum entanglement than to correlations, than to classical correlations and to complex classical problems?
But we're looking at also classical problems like one-dimensional or two-dimensional spins. People are now using. People in the past 2 years have started to use neural networks. They started with RBMs, reduced Boltzmann machines, to start representing complex systems. Very, very recently, in the past year, people are using also convolutional networks to represent complicated systems. Physicists use Monte Carlo sampling techniques, which creates many, many issues. If you look at techniques used in machine learning, you can find ways of overpassing these sampling techniques and doing something much more efficient. These are things that we're discovering very, very recently. So there is a host of techniques that have been developed in machine learning that could be quite relevant to representing complex systems, both quantum and classical.
More comments, questions? Please. Please speak up.
Yeah,
sorry.
I don't hear you.
I'm not too familiar with tree tensor networks, but as far as I'm aware, the depth there should not give you any added value as opposed to a matrix product state, for example. So why do you claim that depth there helps? They have the same amount, they should both obey the same area law.
So when you look at machine learning, right, you can create a network, a mapping from input-output using a shallow network, and that shallow network would be universal. You'll be able to represent any mapping from input to output. And you could do the same thing with a deep network, and it can represent any mapping from input-output. Now, if you want to represent any mapping from input-output, also a deep network would need to grow exponentially large in order to represent any mapping from input-output. So then the natural question is why deep matters. It's not that, to represent any function in a deep network, you'll need only polynomial number of parameters with a shallow exponential. And the point is that if you look at functions represented by a deep network, those functions, up to a measure 0, so almost always, those functions would need an exponentially sized shallow network in order to represent it. Okay, so this is in the machine learning. Okay, so what I've shown is we use techniques from quantum mechanics, this quantum mean cut, in order to prove that claim in machine learning. I didn't claim the opposite. I claimed let's look at quantum mean cut as a tool to prove the depth efficiency in machine learning.
But you can do the same thing with an MPS, right? Like the tree tensor network, which does not have depth.
Well, MPS is, in the language of tensors, it's called tensor train. So there is a complete analogy between tensor decomposition in tensor network and architecture of tensor networks. So a tree tensor network in the tensor community is called a hierarchical Tucker decomposition. So in decompositions, you are doing linear combinations of autoproducts. In tensor networks, right, you're doing contractions. Now, the equivalent of an MPS is a decomposition called tensor train, right, where you're kind of creating a sequence. Now, the expressivity of a tensor train and expressivity of a hierarchical Tucker is the same. No one claims that one is more expressive than the other. And also, efficiency between them is also the same. One does not claim that a function represented by a hierarchical Tucker would require an exponential-sized tensor train in order to represent it. So between a tree tensor network and an MPS, there is no efficiency. It's not that one is exponentially more efficient than the other. This is not something that I claimed. I claimed between a deep tensor network, tree tensor network, and a shallow tensor network. This is where this exponential efficiency happens. Okay.
Last question, please, Roy.
You've shown a mapping between functions in constrained solution space and wave functions in constrained Hilbert space,
yeah.
If you like. And I guess optimizing one would correspond to optimizing the other with respect to some operator in this Hilbert space. So would a quantum computer operating in a constrained Hilbert space be useful in order to find the correct function in the AI problem?
It's an interesting notion. I need to think about it. Like, I cannot say yes or no, but it's an interesting notion. So actually, you made this talk very interesting to me now.
Okay, so you also got something.
I also got something, yes.
Okay, so let's please thank Amnon and all the speakers of today.